going to move this out of the way. So divide by, I guess I'll use a nicer looking fraction bar. Divide by 10 meters per second squared. And I still need to move this out of the way. So the height comes out to 33,500. Yeah, some kind of unit here. I would have to make a whole unit analysis. The joule is actually kilograms meter squared per second squared, and then we can see, okay, these divide out, the kilograms divide out, and then one of the meters divides out, and we're left behind with meters. So hypothetically, if we drop that chunk of ice from a height of 33.5 kilometers or 20 miles up, then it would melt upon impact. What it kind of shows here is that, besides that it's kind of ridiculous and totally hypothetical, is that the latent heat of fusion for ice is quite big. In order to provide that much energy, in this case potential energy, you have to lift to a very large height to provide that much energy just to melt it. Of course, we use different means to melt ice or to solidify liquid water. But it's a huge amount of energy because the latent heat of fusion and the latent heat of vaporization are very large, and the specific heat capacity for water is large. The latent heat of vaporization, we know that it's very large because it takes a long time to totally evaporate a pot full of liquid water. Chapter 17, number 7. It says a 10 kilogram iron ball is dropped onto a pavement from a height of 100 meters. So we have 10 kilograms of iron. If half of the heat generated goes into warming the ball, so 50% efficiency, that means probably the other 50% is used to warm the pavement. Find the temperature increase of the ball, and the specific heat capacity of iron is given as 450 joules per calorie and joules per kilograms and Celsius degrees. That's equivalent to the 0.11 calories per gram and Celsius degree. Why is the answer the same for a ball of any mass? Well, let's see what happens from a height of 100 meter. Oh, I guess I didn't write that down yet. So height of 100 meter. Okay, again we have a certain amount of potential energy, of which 50%, so 0.5, will be converted into heating the ball, so that equals Q. And then we have the potential energy given as mass times gravity times height, and here we have specific heat capacity times mass times temperature difference, and the mass divides out, so we actually don't need the 10 kilograms. That's why. That actually answers the second question. The temperature difference here is independent of the mass. Oh, I almost forgot that 50% efficiency, so there's a 0.5 in the front here. So 0.5 times 10 meters per second squared times a height of 100 meters, that's about 300 feet, equals 450 joules per kilogram and Celsius degree, and then times whatever temperature difference we're going to calculate. So delta T, that delta T over here equals everything over here divided by the 450. So delta T equals fraction bar 0.5 times, that's not a minus, that's a times 10 meters per second squared times 100 meters divided by 450, Ooh, and here comes the joules. Kilograms meter squared per second squared. Divide that whole thing by kilograms and Celsius degrees. Okay, let's see, kilograms are dividing, the second squares are dividing, the meter squared right here, there's a meter here and there's a meter there that they're dividing with, and the only one left is divide by a fraction which has the Celsius degrees in the denominator, so that means that the Celsius degree will turn up on the top, and then we have 0.5 times 10 is 5, times 100 is 500, 500 divided by 450, you may do that on the calculator, comes out to around 1.1 Celsius degrees. So it does increase a little bit in temperature.